Let's start. So our next speaker is Professor Chenjie Wang from University of Hong Kong, and he will present his awarded paper on braiding statistics of loop-like topological excitations in 3 dimensions. Let's welcome Professor Wang.
Okay, thank you. It's my pleasure to be here. So this talk is about this, mainly about this work, which was done 10 years ago. So I will mainly review some of the progress. If you are expecting anything new, I'm sorry. So most of the works are done a few years ago. Maybe the earliest is like 3 years ago. So I will basically introduce the concept associated with braiding statistics of extended objects in 3 dimensions. So let me give you a brief, brief recap on what is braiding statistics in 2 dimensions. Before we actually talking about the braiding statistic data, actually we first need to talk about the process, the physical process, which one we are examining. There are basically main fundamental process. One is you braid one part, so consider a mini-body system with an energy gap. So you have point-like excitations. So you can do, one process you can do is you make a full braiding of one particle, here denoted as alpha and beta, okay? Another process, if you have 2 identical particles, you can make an exchange. So associated with these 2 processes, we can have mutual statistics and exchange self-statistics, and also called exchange statistics. So the data depends on, associated with these processes, depending on the precise nature of that particle, okay, quality particle. So if they are, the exchange statistics is 0 or pi, and the mutual statistics is 0, then it's well known. They are called, fermions and bosons. 0 for boson, pi for fermion. It's well known. And more exotic cases can happen in 2D. If associated with this braiding process, the many-body wave function and acquire a phase factor. Okay, this phase factor is actually more generally, in any process, you actually can have dynamical phases, geometric phases, but also topological phases. So by stating this process, I actually mean the topological part of the phase associated with this process. So when this phase is non-zero, okay, more different from the fermion and the boson case, it's called abelian NAM. And in more general cases, when we have a bunch of particles in this mini-body system, and there could be degenerate Hilbert space associated with this set of particles. And a braiding process may do a unitary transformation, which in this case is not a phase factor anymore. It will be a matrix. And in this case, because braiding is non-commutative, so they are called non-abelian NAMs. Okay? So now, if we go to 3 dimension, so there are 2 kinds of topological excitations you can imagine, particle-like and string-like. And because of certain conservation law, they must form closed excitation. And the simplest one is a loop. Okay, you may consider more complicated ones like knots, links. Okay, but the fundamental ones are point-like particle, and this loop. So because of these 2 fundamental topological excitations, you may consider 3 kind of processes. Okay, exchange between particles. Okay, also full braiding between particles. But in 3 dimension, we know that the full braiding must be trivial. So the non-trivial one is only this exchange process. You may also consider braiding between particle and loop, then between loop and loop. Okay, this was the stage before we did the work in 2014. And in 2014, so we considered a more complicated process. There are certain reasons which I'll explain later, but we discovered that this process, which involves 3 loops, okay, and they are actually linked. So the process is you braid one loop around another alpha and beta, while there is a third loop threading both of them, the alpha and the beta loops. Okay, so this is stuff that we did. This talk is mainly about understanding this process the braiding statistic data associated with this fundamental braiding process. I should point out that there is at the same time, there's another work by actually the host and his collaborators. They also studied a similar process, but from a slightly different perspective at the same time, independently. So after this discovery of this process, in the last 10 years, there are many works. People are trying to understand the physical properties of this loop braiding process, as well as applications, applications of this three loop, which we call three loop braiding. So there are different methods. So like algebraic methods based on category theory, etc. And also using exactly soluble model like Dijk-Witten models, Crane-Yetta models, also continuum topological field theory. In 3 dimensions, there's no Chern-Simons theory, so you go to something called BF theory, and also people use a nonlinear sigma model. There are some other kind of, so this is like a purely lattice model construction. This is purely continuum field theory. There's also kind of a mixture. In certain direction, it's continuum. In some other direction, it's a discrete, so some layer construction. So these are kind of these works. It's not a complete list. Sorry if I missed some of the work. So, but anyway, just to give you a flavor that there are different methods that you can use to understand the properties of this physical process. Okay, so this is basically the general so the warm up of this talk. So basically, I won't talk too much about this three loop. I will so today I will basically introduce some basic concept of three loop process. I will just let you know one of the reasoning why we are led to this slightly more complicated process beyond the particle loop and the loop. Okay, there are and also some example which shows that this it is indeed it's necessary and it's actually important for us to consider such kind of process. Then we talk about some application to characterize three-dimensional so-called symmetry-protected topological phases. I will briefly mention both bosonic and fermionic phases. They are slightly different. But anyway, let's go on. So to be concrete, okay, I will discuss these particle-like and loop-like excitations in the context of discrete gauge theory. Okay? And moreover, the gauge group, sorry, not very good used to this. So I will consider the abelian gauge theory. So this one will be simpler. So consider a general abelian group. This group structure is just a Zn1 cross Zn2 cross Znk. There are k components. So and we can assume that this lattice gauge theory is a deconfined. Okay, it's not confined. So all the particles they can move freely, and also it's energetically gapped. So it's a gapped mini-body system with the charge and flux is free to move. So the gauge charges are labeled by an integer vector, Q1, k component vector. And these k's are defined modulo, and Qi is defined only modulo Ni, because it's the N gauge theory. So the charges are well defined only modulo N, okay, depending on the component. So they are point-like excitations. There are also fluxes. You can imagine they are just magnetic fluxes. But this is not U1 gauge theory, so these magnetic fluxes, they are discrete. Taking this natural unit h bar equals c equals 1. So the fluxes are basically a fraction of 2 pi. Okay, the fraction is some integer divided by n1. This c is not speed of light; it's just some integer. So you can label these fluxes and the charges. So in general, a flux we can also consider a composite between a flux and a charge. So in the context of two-dimensional lattice gauge theory, this kind of objects usually are called dyons. But one thing is in 3 dimensions, so you may consider more general discrete gauge theories, so that these particles will be non-abelian. They are labeled by representations of the irreducible representations of the gauge group, and the fluxes are by the conjugacy classes. But here we are limited to abelian gauge theory. And the one concept maybe you can also think of is so you may consider the total charge carried by the flux, and which physically can be understood as if you shrink this extended object to a point, it will become a charge, okay? So for the abelian case, it's very simple, this shrinking process. But if you go to non-abelian gauge series, this process it will be slightly more complicated. The outcome is not unique. Oh, here. Yeah. N1 on N1 loops. So are you talking about like on one loop you have multiple charges? Yeah. Then I will only care about the total charge, because later, as we will see, that only the total charge will affect the braiding statistics data that I'm interested in. Okay. Yeah. So this position. So here, keep in mind that so my purpose here is trying to define certain topological data. Okay. You may consider details that depend on the position, but eventually so you may define something. If you are able to define certain topological data that depends on the position, that's probably something new. But here, the one that we define does not depend on the position. Okay, it only depends on total charge. So you put this charge randomly anywhere. Okay, and so that's the setup of the topological excitations. So now consider these three processes. Okay, so the particle. So these are the charges. Depending on, so the charges in the gauge theory language, they're called matter, okay? Depending on whether this matter is fermionic or bosonic, these particles are fermionic, bosonic. But for this moment, let's keep in mind that, let's assume that everything is bosonic. That will be simple, okay? So then charge loop braiding will be the famous Aronoff-Bohm phase. Okay? You move one particle around the flux, you got some Aronoff-Bohm phase, which is given by the dot product between this charge vector and this flux vector. Quite simple. So now you may think, okay, so this two process. So this is originally, when we were thinking why we go to three loop. So the reason is you can somehow argue that this two loop process, which this process, let me describe a little bit. I think I have some animation. Yeah, so you have this first loop shrink a little bit, pass through the second one, then you expand, wrap around the second, the beta, okay? This is the process. So you ask the question, are there any possibility that we can define some topological phases, assuming everything is abelian at this moment? So it's a phase vector. So is it possible that we define something? Okay, for simplicity, let's first consider the case that these loops are neutral. According to my definition, neutral means that if you shrink this loop, there's no charge attached. When you shrink it, it becomes nothing, okay? There's no charge. So this is only well defined when we are in 3D, because these loops are, you can create a loop or annihilate a loop locally, not locally, but completely. But if you consider two-dimensional gauge theory, if you only consider one point flux, which you actually cannot do that. So, but anyway, so we consider neutral loops and understand what kind of phase can we associate with it. But we are considering topological processes, or the data associated with some process, okay, topological data. So in order to do that, so let's try to, okay, this is a process, okay? So now, by topological, we mean that there are some data, hopefully this phase vector, which shouldn't depend on the path, okay? We can smoothly deform the path. So we can do this. We shrink it a little bit, so the path becomes narrower, Then we can further deform it. Okay. So deform it in a way that it actually, this one in the middle is nothing. In the case that the alpha actually shrinks to a point, then it's gone. And this is possible because we assume this loop is neutral. Then it reappear on the other side, then wrap around. Okay. But in this case now, we can further shrink this beta. It's gone. So this whole process that I'm doing here is smooth in the sense that the two bodies associated with this process, alpha and beta, they never touch each other. Okay, so that means it's smooth, and the end result is that alpha is braiding around nothing. Okay, so that means this if there's any topological phase that we can define, it should be zero. Yeah, no charge attached. So, but this is a special case, right? But this special case we are allowed to prove. I'm not sure how mathematically rigorous it is, but intuitively it's the case, right? So it should be 0. So now you can go to more general cases. So by attaching some charge to it. But in this case, because we assume everything is abelian, so you would expect a certain kind of linearity in the sense that braiding this alpha attached with charge around beta attached with charge, this process can be decomposed into the flux, the loop around this loop, the neutral around neutral loop, this charge around the loop, charge around charge, and this loop around this charge. Okay, there are 4 components. Okay, so that means, this charge, we assume everything is boson in this case for simplicity, and even if it's fermion, the full braiding should be trivial. And also loop, the neutral loop will be also trivial, we just proved. So what's left are just the charge loop and loop charge, which are given by the Aronoff-Bohm phase. Sorry? They share, I mean, no, they don't share. So here I'm only considering topological part. There's no interaction. So by interaction you mean the energy. So here we don't consider energy. So energy, so there's an energy gap. All our processes that we are doing is well below the energy gap. So you can consider that's the adiabatic process. I'm not sure if I understand your question. Okay. So the end result is that for a general loop, what you can define is the phase vector, but this phase between 2 loops, this phase is completely determined by the Aronoff-Bohm phase. So that means, okay, there's something new, but there's some data you can define, but it's not something new. Okay, it's completely determined by the Aronoff-Bohm phase. Okay, so now, but there are motivations behind, so we have some motivations that we want to find something new beyond this Aronoff-Bohm phase. This motivated us to understand this 3-loop process. Okay, the braiding between alpha and beta is exactly the same, but what we do is now an extra feature is that we have an extra loop threading through both alpha and beta. So because of the existence of this, we call this base loop, because of the existence of this base loop, so now this previous argument that I was giving, you shrink these loops to a point without touching other body in this process, it does not work anymore because this gamma, if whenever you try to shrink alpha and beta, you will always touch this gamma. Okay, so in principle, there could be something new. Okay, so this is the process. So now we are at the stage that this possibly be a new process, new physical process that can lead to new topological data that we can define. Similarly, we can also define exchange process. You have 2 identical alpha, you can exchange them. Okay, that's well understood. Okay, so now maybe before I give you an example, I will just list a few without explaining too much about the properties of this. But by the way, I denote this 3-loop process between as a alpha braid around the beta with this base loop gamma. So there's a comma, so theta alpha, comma gamma. Okay. So there will be certain physical properties that you suppose this theta is defined. You can try to understand. For example, alpha braid around beta should be the same as beta around alpha because this process they should be symmetric. And also, braiding 2 identical alphas in a full circle should be the same, should be twice of the exchange. Okay, exchange, if you exchange, then you further exchange. Okay, it's basically twice of the full braiding. There are also, certain compatibility issue between braiding process and the fusion process. For example, so there is a base loop, this gamma, which I didn't show the full circle. We should close up. Okay. But if you are trying to braid, alpha around beta 1, then further around beta 2, then this braiding process should commute with the fusion process in the sense that we braid around both alpha and beta and further fuse beta 1 and beta 2 into the sum. Okay, this fusion outcome I denoted as beta 1 plus beta 2. So this one is easy to understand, but there is a slightly more complicated fusion. You can this one is like a fuse alpha, beta 1 and beta 2 horizontally. But there's also some other process if you consider alpha 1 around the beta 2 while the base loop is gamma 1. Another is alpha 2 braid around beta 2 with the base loop gamma 2. And you can try to fuse alpha 1 and alpha 2 as well as beta 1 and beta 2 vertically, okay? Then you will have something, I will use this notation, circle plus. And somehow if you try to draw some diagram, you'll find that this fusion process and braiding process, they commute, which leads to this kind of equation. I will not go into too much details into how we derive, and in any way it's incomplete, but just trying to give you some kind of flavor how you can manipulate these braiding processes. And there are some fundamental constraints associated with these different braiding theta. Okay, but so far I'm just saying that, okay, we can possibly define this new data, but whether it's really new or not, maybe there exists some other argument which we haven't found that leads to the conclusion that this new braiding statistics is also trivial, okay? So we need, in order to exclude this possibility, we need to really compute some example. So we actually go to the case of a Z2 cross Z2 gauge theory. And there are actually 4 types of Z2 cross Z2 gauge theory. The gauge group is just Z2 cross Z2. And these 4 types of gauge theories are actually constructed quite some time ago by Dycroft and Witten. And the 4 theories are labeled by an element in the 4 cohomology group associated with Z2 and Z2 cross Z2. So you can try to compute it. You find that this is some mathematical object, but without going into detail, I just say that this is a parameter in this model, and there are 4 choices you can take, okay, depending on the. So these 4 choices leads to they're labeled by actually, in the simplest possible labeling scheme, you can just label them by P1 and P2. These are 2 integers. They can take value 0 and 1. So if you put into this model, sorry, I don't write on this model, but it exists and it's exactly soluble, in fact. So you go there, and because it's exactly soluble, so you can try to design certain process, this is a 3-loop process, and extract the data. Fortunately, that's a topological field theory, actually. So then no geometry, no dynamics at all, and eventually the data that you extract is purely topological. So this is the end result. So by the way, I should clarify my notation, because this is Z2 cross Z2 gauge theory. So if the fluxes, so it can label them like by this 2-component vector. Okay, but this Z2, so the flux is either pi in the first component or pi in the second component, or maybe a combination, the composite of them. I will call this one the type 1 unit flux, and this one a type 2 unit flux. So this notation means that this exchange statistics of 2 type 1 unit flux with the base loop also being type 1, okay? You can then other notations are similar. You can extract the data. Then you find that this 3-loop exchange statistics depend on P2, P1. So by the way, this plus minus exists because I haven't specified the charge attachment. Okay, I only say that this is type 1 flux. You can add some charge onto it, but because this is Z2 gauge theory, so the charge will give us a pi Aronoff Monn phase, which is a plus minus sign in this notation, okay? So this plus minus sign coming from, it's all everywhere, so it's coming from the charge attachment. But the important thing is that, depending on whether P1, P2 is 0 and 1, this one could be, plus minus 1 or plus minus I. So that's the difference between, the 4 types of gauge theories. So that justifies, okay, indeed, this 3-loop process is a new physical process that we should consider. And associated with this abelian phase is something that could characterize 3-dimensional topological phase of matter. Okay, Oh, by the way, so this data, there is you can try to directly compute this from the exactly soluble model, but there is a more intuitive way in terms of understanding it using the so-called symmetry protected topological phases. This is a one slide, very quick introduction to three symmetry protected topological phases. Okay, I'm trying to give you an intuitive understanding of this data. Okay, so symmetry protected topological phase is some kind of a phase with no anyons, no topological excitation at all, but there are some short-range entanglement protected by the existence of by the requirement of symmetry. And there are some non-trivial topology inside the bulk. They can be defined in any dimension, 2-dimension or 3-dimension. And non-trivial things happen on the boundary. Depending on the dimension, you may have the boundary spontaneously break the symmetry or be in a gapless, sometimes a conformal field theory, okay? Or sometimes in higher dimensions, it can be a topological order. So there are different kind of symmetry protected topological phases. And in fact, this data is actually also labels symmetry protected topological phases with Z2 cross Z2 symmetry. And this Dycroft-Witten theory is the gauged version. If you try to gauge the global symmetry, meaning that you couple this SPT matter with this corresponding Z2 cross Z2 gauge theory, you got the Dycroft-Witten theory. Okay. So now, how to understand this appearance of this theta? Okay, one very intuitive understanding is that so it rely on our knowledge of 2-dimensional. So we are considering 3-dimensional phases. So if you understand, so one kind of result that we have is in 2D. If there's only a single Z2 symmetry, there is a non-trivial SPT. Okay, there is trivial or non-trivial SPT. So now what we can do for this 3-dimensional phase is, suppose we insert a type 1 flux. Okay, type 1 means that associated with the first Z2, the unit flux. And there is a branch cut. Okay, this is, you imagine that this is a magnetic flux line. So in order to insert this flux line, there should be some branch cut. Okay? And this branch cut, you can imagine that it is some kind of imaginary 2-dimensional system. And this 2-dimensional system may or may not be the SPT state of the second Z2. Okay, we call that this is a type 1 flux, and this branch cut may or may not have a Z2 SPT of the second Z2. So when this is the second Z2 is non-trivial, it actually, maybe next slide. So when now, suppose that it's non-trivial, then you can further insert a flux of the type 2 unit flux. And you can try to consider, or maybe you can insert more type 2, for example, more type 2. Then you can try to understand the exchange statistics between type 2 linked to this type 1 of, you can understand it as the base loop in our 3-loop process. Okay, the result coming from 2D is that if this 2-dimensional SPT is non-trivial, then the exchange statistics between this flux line should be plus minus I, or in words, it's semionic. Okay, semion means half fermion. It's semionic plus minus I. So this is basically, the appearance of this, the exchange statistics of type 2 with the base loop to be 1 exhibit plus minus I when P2 is 1. Okay, the semionic statistics. And there is another, the dual kind of case is that you have a type 2, but whether you stack a type 1 Z2 SPT or not. And these two attachments, they are actually independent. So this leads to these two kind of non-trivial data, and which corresponds to the two types of, the combination of them gives us this 4 Z2 cross Z2 gauge series. Okay, so all these things, what I'm saying now, this is I have given you the definition of this 3-loop process, as well as one example, which demonstrates the non-trivialness of this braiding process. Okay, so I think that's already. I think it's this is the most important part of the this talk. So the rest, I think, will be very quick. So now I already said that this Z2 cross Z2 can be distinguished by checking the 3-loop process. So more generally, if you are trying to understand the symmetry protected topological physics with arbitrary fermion, arbitrary abelian symmetry, you can try to define something what we call topological invariant, because in the table that I give, there's this plus minus sign, which is coming from the Aronoff-Wang phase, which are not useful in terms of distinguishing SPT phases. So you can define certain composite three-loop braiding process, in the sense that not just braid one loop around another, but you braid one around multiple times to get rid of this extra plus minus sign, which are some redundant information. Okay, I'm telling you that you can do that. So in the sense that now you can consider certain, same as before, some unit fluxes, like a type I unit flux, type J unit flux with the base loop to be type L. Then you do a composite process, multiple times, and this multiple time actually is the least common multiple of Ni and Nj, okay, depending on the I. So, and this is good quantity, okay? If you believe me, this one will be independent of charge attachment. You can further define other quantity like this exchange statistics. But by the way, I need to point out that even if this gauge group is abelian, this loop braiding statistics can still be non-abelian, in the sense that for certain configuration of the loop, the many-body state may be degenerate. Then when you try to braid around these loops around another loops, you may have a non-abelian braiding. So in this sense, in general, the exchange statistics is not sometimes it's not a good, it's not well-defined quantity. And we need to go to something called equivalent definition called topological spin, meaning that instead of exchange 2, but actually rotate the spin by 2 pi. And we rotate it by n times, you can also get rid of charge attachment. I won't go into details, but just trying to say that there's certain quantities you can define. There's another quantity which is associated with the commutator of certain braiding processes. You braid one around another, then this alpha around beta, this type I around type J, then type I around type K, then do the reverse order. This is basically commutator. And all these things, these quantities are well defined, independent of charge. They can even detect non-abelian statistics in abelian gauge theory. Okay, so with all these quantities defined, then we can go to general SPTs or general Dickerf-Witten theories. They are also labeled by this focal cycle. Okay, and explicit data of this focal cycle can be given. It's too mathematical. If you don't know, it doesn't matter. You can just understand this is the input data of different gauge series. And in fact, it exhausts all possible different gauge series. And then you can plug into this exactly soluble model and extract the three-loop process. In fact, this topological invariant defined through composite three-loop braiding process. And this data, we can show that there is a one-to-one correspondence between the class of gauge series, number of the gauge series and the topological invariant. So in this sense, this three-loop process is complete, okay, for abelian gauge theory, complete, okay. That means we don't need to go to more complicated topological excitations like loops, knots, okay. But this is only for abelian gauge theory. And this is the example. I won't go into details, but I think it doesn't matter. I already made a claim. So we can also incorporate fermion particles. So this is slightly different for abelian gauge theory. So when the particle is fermion, we can still define this topological invariance theta I L, theta I J L, theta I J K L. But there's one tiny thing is that this the one associated with the exchange statistics or the non-abelian version, which is the topological spin. There are some kind of even odd effect, which you can imagine that because fermions you have 0 and pi. So I'm sorry, I won't expand it because I only have like 1 minute. So anyway, I will just, my point is that we can define similar quantities, and these similar quantities can be used to distinguish different fermionic symmetry protected optical phases. And in fact, this is a table that we actually obtained for some simplest possible examples. And there are certain new phases and that we can, this is not from it's not extracted from exactly soluble model. It's actually extracted by studying these consistency equations of the topological invariance, which I won't. Yeah. Anyway, maybe one thing is that, for example, consider this one example. So there is this one is called fermion parity. This is a symmetry. It's a symmetry for every fermion system, because in fermionic systems, in the Hamiltonian, we cannot add a single fermion creation annihilation operator to it. We must add the pairs of them. So there is always this Z2F symmetry. But with the extra symmetries, okay, so you can imagine this one, Z2 cross Z2. If you forget about this Z2F, then this is the example that I was talking about. Okay? In the case that we have a bosonic SPT Z2 cross Z2, but even if we embed this bosonic system, SPT into a fermion system, we won't get anything new for Z2 cross Z2. But if you enlarge the symmetry, you will get something new. Okay, so these Z2 cross Z2 are the one that I was talking about. But you got some extra ones, which is intrinsically fermionic in the sense that they don't exist in bosonic systems. They are new because when I say we embed bosonic system, so in the sense that so if you have a bosonic system, suppose your bosonic molecule is actually a pair of fermions. So the question is basically whether you always consider this pair as a boson, or you are able to separate them, whether you can have something new or not. So these are basically saying that if your bosons are actually made out of two fermions, then you will actually have something new. And this one actually is not hard to understand in the sense we can still use this decoration picture. So forget about this fermion. So we have two symmetries. Now we can insert a flux associated with this Z8 unit flux. Then you may imagine whether there are some SPT phases associated with the second symmetry, which is Z2 in the current case. Fortunately, why we pick Z8? Because the SPT classification of the other Z2 has a symmetry, has a classification Z8. The classification of the 2D SPT is compatible with the symmetry group. So the SPT of this Z2, which is Z8, matches this base loop Z8, and eventually you make something interesting. But this D8 has some interesting feature, is that when in this Z8 classification, the smallest, the root state actually carries a flux, in the sense that if you imagine this is some kind of P-wave superconductor, then you insert a Z2 flux, under this Z2 flux you will have a Marana zero mode, okay? This will happen in the case for this setup, except now we have a Marana mode which is spread through this whole loop. And the other one is also spread through this whole loop. So there is a pair of Marana zero mode with one on this loop and another on this loop. And this can happen only when they are linked. If they are not linked, suppose they're trying to have a one Z8 flux loop and another Z2 flux loop, and they're not linked, then sorry, no Marana. But when they are linked, there is a pair of Marana shared between the two. Okay, this is a physical picture associated with this. I think I will be very, so this talk is basically just trying to send you this message that three-loop braiding statistics and associated with other topological invariants that you can define, they actually serve as a topological order parameter. If you imagine in Landau order parameter, we need some kind, before we construct any theory, we first need an order parameter, right? So this three-loop process is this order parameter, and the data you can consider as describing different topological phases. Okay. Last but not least, okay, one page. So I've been saying that this three-loop process is complete in terms of distinguishing SPT phases, three-dimensional SPT phases with a abelian group. But in general, whether it's true or not, I don't know. And in fact, there are not many works that goes beyond the abelian gauge theory. There are a few non-abelian gauge group, and people are trying to understand the braiding statistics or loops there, but still, I don't think it's complete so far. And more interestingly, you may ask the question, whether this three loop is complete in general in terms of describing, not in terms of classification, okay, in terms of describing, characterizing the three-dimensional topological order. I would imagine that possibly not the case, because there are so many complicated structures in 3D. Why we should only focus on the simplest one and the linked structure. So in general, maybe there could be some, I'm not sure, but in terms of understanding the braiding and the fusion of these complicated topological excitations in 3D may be interesting, but it could be very hard. Okay, so that's all. Thank you very much.
Any questions?
For a nice talk. First, I want to ask, do you have a systematic way to dealing with the charge declaration?
Try to what?
Charge declaration. I mean, speak charge on loop.
I think so. Yeah. Even you mean systematic within, say, gauge theory, or how systematic you want to be?
Yes.
When you say charge, I think possibly it's already within gauge theory. I think that is possible. You can do that. So that so then you can consider shrinking of these loops. Then when you shrink, you will. So when you have a loop, basically, the charge on the loop is a irreducible representation of the centralizer of that group element. But when you shrink, the group is gone, then it goes to the representation of the full group. So there is a relation between the representation of the centralizer and the full group, and you need to understand that that describes how charge attachment goes. But it's a bit technical.
I still have some technical question. Maybe we can discuss after.
Yeah, sure.
If you want to gauge the symmetry, like do the anion condensation type stuff.
Gauge what?
Like gauge the symmetry, or if you want to do anion condensation or a high dimension analog like that, you need to take into account this three-loop braiding. Usually, it's you need to be mutually local, right? So that constraint. So if there is a three-loop braiding, that's an obstruction to gauging the symmetry.
So I'm not sure which symmetry you are talking about. So
yeah, I mean there's a. I mean,
there are in this gauge theory there are symmetries generated by the charges.
Yes,
which is a higher form.
Topological loop operator. So I would call that the symmetry.
Yeah, but if you are trying to gauge the symmetry generated by the loops,
yes,
I think there could be some obstruction coming from the three loop. Yes. Yeah. But I don't know.
Yeah. One more question is that as for the open question, do you know if there's a map from the braided fusion 2 category to the three loop braiding? And well, of course, your question is whether it's a one-to-one in a sense, but at least is there a known map from the data of the braided fusion 2 category to the three-loop braiding?
That I don't know.
Oh, okay.
I think probably fusion 2. So here is braided fusion 2 category. So I would think that braided fusion 2 category could contain more data. But whether contains more data, but whether these data are free in the sense that they are not determined by three loop, I don't know. Maybe they are, for example, you may have two. This is an open question, right? So maybe you have two kind of three-dimensional topological order. They have the same three-loop braiding statistic, but they have different, other data. This additional data. This is in fact, why I kind of ask this open question, because this is something possibly interesting to us. Maybe, yeah.
Or maybe I missed something. Do you consider charge loops in the three-loop braidings?
Charged loops? Yeah, it's considered.
So how the charge?
So in that case, in fact, the charged loop becomes ill-defined. So remember when I try to define a charged loop, sorry, maybe it's not clear. When I try to define charged loop, you need to kind of shrink it to a point so that charge is well defined. But if it's three loop, that means it's already like the loop is linked to another one. So then you can't define, so you have this three loop setup, alpha, beta linked with gamma. Then you ask the question whether this alpha carries a charge, well-defined charge or not. It's actually not it's an ill-defined question. You can only ask, how much charge you attach it. In fact, you are only able to compare like one alpha and another alpha. They both are linked to the gamma, and they may have different charges. That's the relative charge between the two loops linked to the same base loop is a well-defined question. But the absolute charge of a linked loop is not well-defined.
So how does this relative charge contribute to the braidings?
You give the same extra Aronoff bomb phase, which is something that we want to get rid of, when we define this topological invariance.
Okay, thank you.
Because
Another question: does it have some intuition about how do we construct the order parameter if we want to really compute a theory that connects two SPTs?
Order parameter for what?
So if I have theory that connecting two SPTs, then does this three loop braidings have some intuition about how we construct the order parameter?
Construct the order parameter.
That's so we can tell that around the loop we are in the first SPT or the second SPT.
I don't quite understand the question. Sorry.
So if I have a theory that I know connects to SPT around through a flow, so along this flow, is there any other parameter that I can distinguish between SPTs into by the intuition of this?
It doesn't change. It's not like the usual Landau gauge theory. You are probably thinking of I'm not sure if you are in your mind is you have some Ginzburg-Landau theory where you have this order parameter which changes continuously, so that you have a zero, gradually decrease and gradually increase. Here, when as long as you are in the same phase before the phase transition happens, then the order parameter that you are thinking of probably is a constant. So it does not change. So if you are able to define some other continuously, that continuous order parameter, that probably is not a direct it does not give you direct signature of this SPT, but maybe it gives you some indirect signature.
Okay, thank you.
Okay, last questions.
Is this a braiding statistic of?
Good question. Yes. No. I would say within these examples, actually does not. That's a good question. In fact, I haven't thought about very carefully. My intuition is that it does not. Okay, but maybe in certain cases. So when this, at least if this three loop is abelian, then it does not change the ground state degeneracy. But if it's non-abelian, I think someone else, they did some calculation, but I forgot the result. It's something probably worth to check. Yeah. In fact, we are trying to do similar calculation, but for more complicated models, and see whether there's anything new beyond this, or whether this three loop can affect this ground state degeneracy, or whether there are some new data can affect this ground state degeneracy.